Imagine a raindrop falling from 2 kilometers up with nothing to slow it down. It should hit you at over 700 kilometers per hour. That is faster than most passenger jets cruise at. Every drop above you should feel like a bullet, but it does not. The same drop actually lands at around 30 kilometers per hour, slower than a cyclist coasting down a quiet street. 700 kilometers per hour on paper, 30 kilometers per hour in reality. So what happens in between? What steals almost all of that speed on the way down? The answer is a force you cannot see. It pushes back on every drop, every second it falls. And the same force is quietly at work on skydivers, snowflakes, hailstones, even debris falling from space. Once you understand it, you will never look at rain the same way again. Here is what nobody tells you about falling objects. Gravity does not act alone. In a vacuum with no air at all, gravity would just keep pulling, faster and faster, with nothing to stop it. A raindrop falling through empty space would hit the ground at a genuinely lethal speed. But Earth is not a vacuum. It has an atmosphere. And the moment that raindrop starts moving, the air pushes back. This pushback is called air resistance, or drag. Here is the part most people miss. Drag is not constant. The faster something moves, the harder the air resists it. Picture sticking your hand out of a moving car window. At low speed, you barely feel the air. Speed up, and it suddenly shoves your hand back with real force. A falling raindrop feels exactly this. At first, gravity wins easily. The drop barely moves, so drag is almost nothing. It speeds up fast. But as it speeds up, drag grows right along with it. The gap between the two forces keeps shrinking. Gravity still pulls down. Drag now pushes up almost as hard. Eventually, the two forces cancel out. The net force on the drop drops to almost zero. And when that happens, the raindrop stops accelerating. It keeps falling, just not any faster. Scientists call this terminal velocity. Notice what that means for the trip as a whole. A raindrop does not fall at one constant speed from cloud to ground. Near the top of the fall, it is still speeding up. Only later does it settle into that steady terminal pace. The journey down has two distinct chapters, not one smooth motion. So why does a raindrop not just keep speeding up all the way to 100, 200, 300 kilometers per hour? Because of a simple feedback loop working against it the whole way down, the drop speeds up. Drag grows because of that extra speed. More drag means less net force pulling it down. Less net force means less new acceleration. Around and around, until the two forces land almost exactly on top of each other. Picture coasting down a long hill on a bicycle. At the top, gravity pulls you forward and you pick up speed fast. But the faster you go, the harder the wind pushes back against you. Given a long enough hill, you stop speeding up. You just keep rolling at whatever pace the wind allows. A raindrop does the exact same thing, just on a scale you can barely see. Rain is not the only place this shows up. Skydivers hit terminal velocity too. Jump from a plane, and you accelerate for the first several seconds, then drag catches up. You fall at a steady speed, close to 190 kilometers per hour, body flat to the wind. Open a parachute and the surface area increases massively. Drag spikes. Terminal velocity crashes down to a safe landing speed. Same physics. A completely different shape. For a raindrop, the numbers are far smaller. A typical drop levels off somewhere around 36 kilometers per hour, depending on its size. Bigger drops actually fall faster than small ones. Their mass grows faster than their surface area does. More weight pulling down without a matching rise and drag pushing up. Tiny droplets, the kind that make up mist and light drizzle, barely fall at all. They can hang in the air for minutes, pushed around by the smallest breeze. Here is where it gets stranger. A raindrop is not shaped like the teardrop you have seen in every cartoon. Surface tension holds a small drop close to a sphere. But once air starts rushing past it at speed, the bottom flattens out. Push it further, and it starts looking more like a tiny hamburger bun than a drop. That shape change matters, because drag depends heavily on shape. A flattened drop catches more air than a perfect sphere would. Past a certain size, the aerodynamic forces get so strong, the drop simply tears itself apart into smaller drops. That is the real speed limit of a raindrop. Not distance, not gravity alone. A constant tug of war between how much drag a shape can generate and how much weight gravity has to work with. But here's the part that surprises almost everyone. That drop landing on your head right now did not fall in a straight line from a cloud 2 kilometers up. Long before it became rain, it was part of a cloud droplet, something thousands of times smaller than a raindrop, light enough for rising air currents to keep it suspended. Cloud droplets like that do not just sit still. Warm air constantly rises inside a cloud, carrying droplets upward and sideways. It pushes them into each other, again and again. Every collision merges 2 droplets into one slightly bigger droplet. It takes an enormous number of these tiny collisions to build one raindrop. Meteorologists estimate it takes roughly 1 million cloud droplets combining together. That is what it takes to build one drop large enough to actually fall as rain. Only once it crosses that threshold does gravity finally overpower the rising air holding it up. So every raindrop that lands on you has already survived a long invisible journey. A million microscopic collisions, constant merging, growing just large enough to finally fall. It might not even fall straight down. Wind pushes each drop sideways as it descends, which is why rain rarely arrives from directly overhead during a storm. The air itself is not the same the whole way down either. It thins out at higher altitudes and thickens closer to the ground. A falling drop is not moving through one constant medium. It is adjusting to a slightly different atmosphere the entire way. So if a raindrop only reaches 30 kilometers per hour, why does it sometimes sting when it hits your skin? Almost never, really. Speed alone does not decide how much an impact hurts. Mass matters just as much. A raindrop weighs a tiny fraction of what a stone weighs at the exact same speed. That means it carries far less energy to begin with. Shape matters too. A solid object like a pebble stays rigid on impact and transfers its energy almost instantly. Water does the opposite. It deforms, spreads out, and splashes, spending its energy over a longer moment instead of delivering it all at once. Now, compare that to hail. A large hailstone can weigh many times more than a raindrop. It can reach terminal velocities well over 100 kilometers per hour. That is exactly why a bad hailstorm can dent a car roof or shatter a greenhouse, while rain never does. Same physics, same balancing act between gravity and drag. But once mass and density change, the outcome downstream changes completely. That is also why a raindrop and a high-pressure water jet behave so differently. Both are made of the same liquid, yet they act nothing alike. A pressure washer can cut through wood because that water moves at extreme speed, squeezed into a narrow, sustained stream. A raindrop is neither fast enough nor concentrated enough to do that. It is just gravity, air, and a few grams of water moving at a pace the atmosphere has already capped. So the next time it rains, you are watching 3 invisible forces fight it out in real time. Gravity pulling every drop down. Air resistance pushing back harder the faster it falls. Surface tension trying to hold each drop together the whole way. That balance is the entire reason rain feels gentle instead of dangerous. Without an atmosphere, every storm would be a hail of bullets. With one, Earth's atmosphere acts like an invisible brake in front of every single drop. The next time rain lands on your hand, you will know exactly what it survived to get there, and exactly why it never had a chance to hit you any harder. What surprised you most about how rain actually falls? Drop it in the comments. And subscribe. Every week, something you thought you understood turns out to be stranger than you imagined.